Close to 30%. I mean, 30% of all cars sold this year are set to be electric. Think about that for a second.
It's a staggering number, honestly.
Right, it's huge. We were basically watching this fundamental once-in-a-century shift in how humanity moves itself around, and it's happening right in front of us.
Yeah, it really is.
And usually, when we talk about a massive technological shift like this, there's this expectation of a completely seamless transition. You just buy the new gadget, you plug it in, and it just works.
Which I have to say is a very dangerous assumption.
Oh, completely.
It's a bit like upgrading from a landline to a cell phone and just assuming all the invisible cell towers are magically already built to handle millions of new calls.
That is a great way to put it. Because when you step into the world of electric vehicles, that assumption of a seamless transition just shatters almost instantly.
Completely shatters.
So what we're looking at today is a global landscape that is an incredibly complex puzzle. It involves harsh geography, century-old electrical grids, and, well, some really intense mathematical optimization. So welcome to the deep dive.
Glad to be here.
Our mission today is to give you, the listener, a real shortcut to understanding this invisible, highly complex matrix of EV infrastructure. Because, as we're about to see, preparing for these cars is not just about dropping a plug on a street corner.
No, it is far more complicated than that. And we have a really great stack of sources to guide you through this today.
We really do.
We're looking at that headline statistic from an International Energy Agency report, and we're pairing it with this massive federal report. It's the NEVI 2023 to 2024 annual report that stands for the National Electric Vehicle Infrastructure Program.
Right. And then we get into the hardware side of things.
Exactly. We have an industry breakdown by Feyri on global charging standards. And finally, we're going to look at this very dense but completely fascinating optimization paper by Biswar Up Mukherjee, which was published on ArchiSev. It deals heavily with distribution grid constraints.
Sounds heavy, but we'll break it down.
My goal is to connect all these dots so you can really see the whole board.
And we are definitely going to need those dots connected because that 30% stat from the IEA, that means a literal flood of vehicles is hitting the roads right now. So let's start with how the United States is physically preparing for this on a macro level.
A macro blueprint, yeah.
Yeah, the NEVI report, it lays out the federal blueprint. So the bipartisan infrastructure law is pumping $5 billion over 5 years into building out what they call alternative fuel corridors, or AFCs.
And the scale of that ambition really is staggering when you look at the raw mileage. I mean, currently there are roughly 81,000 miles designated as AFCs.
Wow.
Yeah, that covers 37% of the entire national highway system and a massive 94% of the interstate highway system.
But the thing is, the government isn't just handing out billions of dollars to utility companies and saying, like, hey, build them wherever you feel like it. There is a very strict rule attached to this NEV funding.
The 50-mile rule.
Right. These charging stations must be built every 50 miles along the highway, and they have to be located within exactly 1 mile of the highway exit.
And we really should look at why that specific rule exists, because it's not just arbitrary. That 50-mile, 1-mile rule is a psychological tool just as much as a physical one.
Psychological how?
Well, it is designed to completely eliminate range anxiety. By mandating that exact spacing, it creates a predictable cadence for the driver. You don't have to guess if you can make it to the next town. You know exactly what the safety net looks like.
Okay, let's unpack this. Because it sounds great on paper. It's kind of like trying to build a nationwide transcontinental railroad, but having to negotiate the exact placement of every single water tower with local towns and, harsh terrain.
That's a really good comparison.
But just like building a railroad, a rigid map sitting on a bureaucrat's desk in Washington doesn't always survive contact with real-world geography.
It rarely does.
Yeah.
And the NEVI report details exactly what happened when the map met the terrain. The federal government actually had to introduce a system for what they call discretionary exceptions.
Basically a loophole.
Basically, yeah. State planners looked at that strict 50-mile rule and realized that in certain places, it was just physically or economically impossible to meet.
Yeah, the report notes that states submitted 71 requests for these discretionary exceptions, and they were heavily clustered in the rural West. Out of those 71 requests, 38 were approved.
Which, when you think about it, makes total sense.
Right, like if you are driving through a mountain pass in the Rockies, there might not even be a highway exit for 80 miles.
Exactly. Or just consider the infrastructure required. You can't just drop a high-powered DC fast-charging station in the middle of the desert in Nevada.
Just a plug in the sand.
Right, because these stations require an enormous amount of power. If there is no existing electrical grid to tap into out there, utility companies would have to trench miles and miles of high-voltage lines just to power a few plugs.
Which would cost a fortune.
The capital cost would be astronomical.
So they have to compromise. But overall, it seems like they're largely sticking to the grid plan.
Yeah, they are. And if we connect this to the bigger picture, this macro-level planning isn't just about facilitating cross-country road trips for vacationers. It is really about establishing a baseline of geographic equity.
Geographic equity.
Right. By enforcing these continuous corridors, the program actively prevents the creation of charging deserts. This ties directly into the federal Justice 40 initiative.
Ah, I've heard of that.
Yeah, it's a mandate to ensure that disadvantaged communities, whether they're rural stretches or overlooked urban corridors, just aren't left behind.
Right.
Without this kind of forced mapping, private companies would naturally just gravitate toward building infrastructure only in the most affluent, profitable zip codes.
Follow the money. So the billions of dollars are mapping out the highways, creating a safety net, and trying to keep it relatively equitable.
That's the goal.
But mapping the highway is really only half the battle. Because what happens when, say, a European car ships to the U.S. to drive on that newly funded highway? We need to talk about the physical hardware because the actual plugs are completely different.
They're entirely different. The plug you use in North America is fundamentally different from the one you use in Europe.
And according to that ferry article we looked at, it all goes back to a 100-year-old divergence in how we actually built our electrical grids.
It's wild how history shapes this.
It really is. In the United States, our standard grid runs on a 120 and 240-volt system at 60 hertz, but Europe went a completely different direction. After World War II, they largely standardized on a 230-volt single-phase system and a 400-volt three-phase system running at 50 hertz.
And we really need to pause on that three-phase detail because that fundamental difference in how electricity is delivered to a building that dictates the entire design of the plug.
Walk me through that, because I think a lot of us don't know what that means. What exactly is three-phase power, and why does it matter for a car?
Okay, think of single-phase power, like a single person pushing someone on a swing. You get one big push, then there's a dip in momentum, then another push.
Right.
It works, but the power delivery pulses. Three-phase power is like having three people pushing that swing in a staggered sequence.
So there's never a drop.
Exactly.
Yeah.
There is never a drop in momentum. It is a continuous, dense flow of power. And because Europe built that robust three-phase grid reaching deep into commercial zones and even many residential areas, they can push much higher alternating current or AC power.
The ferry article said they can push between 11 kilowatts and 22 kilowatts on just a standard AC charger.
Right, which is huge. And to handle that three-phase flow, European cars use what's called the Type 2 connector. It's often called the Menike's plug.
Menike's, yeah.
It physically has more pins to accept those different phases of power. And for fast DC charging, they use the CCS2 standard, which essentially just adds two larger DC pins to that Type 2 plug.
Got it.
And because the European Union stepped in early and mandated CCS2, it is beautifully standardized across the whole continent.
Must be nice. Because over here in the U.S., since our residential grid is largely on that single-phase system, we've been using a plug called J1772 for AC and CCS1 for DC fast charging.
It has been a bit fragmented.
Very fragmented. Though, as anyone following the industry knows, we are right in the middle of this massive, slightly messy shift to Tesla's North American Charging Standard, or NACS.
Which is now officially standardized by engineers as SAE J3400. And that consolidation is going to be a huge win for consumer convenience in North America, finally standardizing the network.
Right.
But still leaves us with a reality where a U.S. car and a European car are speaking entirely different electrical languages.
Okay, let me play devil's advocate here because this drives me crazy. I travel to Europe for work, I bring my laptop, and I just snap a tiny $10 plastic travel adapter onto my power cord, and my laptop charges perfectly on their 230-volt grid.
I know where you're going with this.
Why can't automakers just sell a simple travel adapter for cars? Why does the internal hardware of the car itself have to be different for different continents?
That is a very common point of confusion. And the answer comes down to the unsung hero of every single electric vehicle.
Yeah.
The onboard charger or the OBC.
The OBC.
Yes. When you plug your laptop into a wall in Paris, that heavy brick on your power cord is actually doing some really heavy lifting.
Hmm.
It is actively converting the wall's AC power into the specific DC power your battery needs.
Right. The brick gets warm, it's doing actual work.
Exactly. In an EV, that conversion brick is built directly into the car itself. That is the OBC. So when you plug an EV into a standard neighborhood AC charger, the charger isn't actually charging the battery, it's just handing AC power to the car.
Oh, wow.
Yeah, the car's OBC does the conversion.
Ah, so the car isn't just receiving power passively, it's actively processing it.
Yes. The OBC is a highly sophisticated piece of power electronics. It contains transformers, rectifiers, and firmware that are all fundamentally engineered to match the frequency of the local grid. Remember, the US grid pulses at 60 Hz and the European grid pulses at 50 Hz.
So if I just slapped a dumb piece of plastic over a European plug to make it fit an American car.
You would have a disaster on your hands.
Yeah.
A passive plastic adapter doesn't change the frequency. If you feed 50 Hz power into an OBC designed for 60 Hz, the transformers inside the car become horribly inefficient.
I'm guessing that's bad.
Very bad. Best case scenario, the car's computer senses the mismatch and throttles the power down to an absolute trickle just to protect itself.
And the worst case?
Worst case scenario, the internal temperature spike and you catastrophically fry the power electronics.
Oh, wow.
That is why automakers literally have to build entirely different regional variants of the exact same car model. The adapter is hardwired into the vehicle's architecture.
That makes so much sense. The plug is just the handshake, but the car is doing the digestion.
Exactly.
So, we've mapped out the highways with the NEVI billions, and we understand why the physical plugs look the way they do based on a century of electrical history. But none of that matters if the local neighborhood grid collapses the moment you plug your car in.
Which is a very real threat.
And that local strain brings us to the ArcSiv optimization paper by Biswarup Mukherjee.
Yes, this is where the abstract physics of the electrical grid collide with the harsh economics of building real-world infrastructure.
It's a very dense mathematical paper, but the insights are wild. So, to test how a neighborhood handles EV traffic, the researchers modeled something called a 14-bus medium voltage test grid. We should probably translate that. What is a bus in this context?
Right, in electrical engineering, a bus isn't a vehicle. It is a central connection point, a node, where multiple power lines meet to distribute energy.
Like an intersection.
Think of it exactly like a major intersection for electricity. Power comes in from high-voltage transmission lines, steps down to medium voltage, and hits these 14 different intersections before flowing out to individual homes and businesses.
Got it. So they built a mathematical simulation of a typical neighborhood grid with 14 main intersections, and then they simulated a fleet of between 250 and 600 EVs moving through this grid, going from home to work, and needing to charge.
They let an algorithm search for the absolute optimal way to build the charging network for those cars. And what they uncovered is a massive systemic trap waiting for city planners.
The CapEx trap.
Yes, it is the trade-off between capital expenditure, which they call CapEx, and actual service quality.
This was fascinating to read. The algorithm showed that if your only goal as a utility company or a developer is to minimize CapEx, meaning, you want to spend the absolute least amount of money on installation, trenching, wiring, and transformer upgrades, the math aggressively tells you to cluster all your charging ports together in just a few massive hubs.
It makes perfect economic sense for them. Trenching through concrete to lay heavy copper wire is incredibly expensive. If you just dig one giant hole, upgrade one central transformer, and put a whole bank of 20 chargers right there, your CapEx drops significantly.
But the paper reveals that the consequence of that cheap, clustered deployment is terrible service for the actual drivers. The simulation found that this spatial concentration leads to a much lower achieved state of charge.
Right.
People are getting the juice they need, and there is a high rate of unmet energy demand.
It creates a physical and electrical bottleneck.
Okay, let's unpack this with an analogy. It's like a grocery store deciding to put all 20 of its checkout lanes crammed into one tiny back corner of the building just to save money on wiring for the cash registers.
That's a great visual.
Sure, the corporate office saved money on construction, but now you have massive customer bottlenecks, people waiting in line, and angry shoppers abandoning their carts because they just can't get through the lane.
That is a perfect analogy. And what's fascinating here is that the Mukherjee paper mathematically proves that cost-optimal planning alone is dangerously insufficient, because the researchers also modeled the alternative.
What happens if you don't cluster them?
Right. What happens if you stop worrying so much about the upfront cost and you take those exact same number of charging ports and distribute them uniformly across all 14 intersections of the grid.
Let me guess. The corporate office hates it because it costs more up front.
It definitely costs more upfront. But by distributing those chargers uniformly, you reduce the energy shortfalls by up to 74%.
74%. That is a massive gain in efficiency for the drivers.
It really is. But from an electrical engineering standpoint, this raises an important question about how we manage grid stress. By avoiding those massive megaclusters, you're practicing what the paper brilliantly calls a passive congestion management mechanism.
I love that phrase, but we definitely need to break it down. What does passive congestion management actually look like for the power grid? The paper mentioned it relieves pressure by up to 0.20 per unit of peak demand, which honestly sounds like textbook jargon.
It completely does.
Yeah.
Let's translate that into something visual. Imagine a single neighborhood transformer on a hot summer day.
Okay.
If you put a massive cluster of fast chargers on that one transformer and 20 cars plug in at 5 p.m., you draw a colossal, concentrated spike of power.
Everybody charging at once.
Yes. That transformer is going to heat up rapidly, and you run the risk of literally melting the equipment or causing a localized blackout. That 0.20 per unit figure essentially means a 20% reduction in stress at the most vulnerable points.
So instead of melting one transformer, you are spreading that exact same electrical demand across multiple different transformers throughout the whole neighborhood.
Exactly. You're using geography to solve an electrical problem. The grid doesn't sweat, and the drivers actually leave with full batteries.
Okay, so we have to fight the instinct to build cheap megastations if we want the local grids to survive.
Absolutely.
But this naturally brings us to a variable that might throw all this careful math right out the window. The cars themselves are changing.
Yes, the battery capacity tipping point. Consumer behavior is shifting rapidly, and it is putting immense pressure on the infrastructure.
Because everyone wants more range. I mean, nobody wants a car that only goes 150 miles. They want a battery that can do 300 or 400 miles.
Naturally.
The Mukherjee paper ran a sensitivity analysis on this exact scenario. They compared their simulated fleet running on 20 kilowatt-hour batteries against a fleet upgraded to 40 kilowatt-hour batteries. And the results completely blew up my assumptions.
You would normally assume a linear progression, right? Like if the average battery size on the road doubles, you just need to double the number of chargers.
Right. But it's not linear at all. The paper explicitly notes that infrastructure growth is sublinear, and it forces a complete regime shift in how the local power grid behaves.
It fundamentally changes the math.
The researchers explain that when the fleet relies on smaller 20 kilowatt-hour batteries, the system is in what they call a port-limited state.
Meaning, people don't need a massive fire hose of electricity, they just need a garden hose. They just need a physical port, a place to plug in while they sleep at home or sit at their desk at work.
But when you scale up the simulation to a fleet with 40 kilowatt-hour batteries, especially at a high volume of, say, 600 EVs moving through the grid, the entire system breaks out of that port-limited state. It abruptly becomes power-constrained.
And we really have to look at the math of human behavior to understand why. It comes down to something called dwell time.
Yes, because a 40 kilowatt-hour battery takes roughly twice as long to fill on a standard AC charger. If you only park at the grocery store for 45 minutes or sit at work for 8 hours, that dwell time simply isn't long enough to fill a massive battery on a slow charge.
Precisely. The cars cannot physically sit still long enough to get full. And because they can't fill up slowly, the system is suddenly forced to rely on highly expensive, high-power DC fast chargers to push that energy into the cars quickly before the drivers have to leave. The infrastructure costs skyrocket. The paper noted that jumping from the 20 to the 40 kilowatt-hour fleet at high volumes caused the required capex to spike by almost 80%, hitting nearly 793,000 euros just for that single local grade simulation.
Here's where it gets really interesting, right? Hold on. As a consumer, I go to the dealership and I intentionally buy the car with a massive battery to fix my personal range anxiety.
Right.
But by doing that, am I actually making the grid's traffic jam worse? I mean, I'm forcing the utility companies to build vastly more expensive fast chargers just to keep up with me.
That is the exact paradox we are facing. Consumer desires for giant batteries and the physical realities of the electrical grid are on a direct collision course. Yeah, if everyone is driving around in massive batteries that demand high-power fast charging because they don't have the dwell time to charge slowly, the local transformers simply cannot handle those localized spikes without catastrophic multi-million-dollar upgrades.
So my desire for convenience basically creates a systemic bottleneck.
It does. And this is exactly why that smart uniform planning we discussed earlier, you know, distributing the load rather than just clustering fast chargers based on CapEx is absolutely vital to our future. We are trying to balance the harsh physics of the electrical grid against human psychology.
So what does this all mean for you, the listener? Well, the next time you pull up to an EV charger, whether you're in the middle of a 50-mile gap on a federally funded interstate highway, or you are just pulling into your local grocery store, you are going to see the invisible
You'll
matrix.
see the whole picture.
Exactly. You will know exactly why your plug is shaped the way it is and how it ties back to a century of electrical history and phase power. You'll recognize that the specific location of that charger wasn't just an accident, but the result of an intense mathematical balancing act between construction costs and the physical survival of the neighborhood grid.
It really is a remarkable orchestration of technology, public policy, and physics.
Yeah.
But if I may leave you with one final thought to mull over.
Please do.
It's a variable that wasn't even the main focus of our sources today, but it looms over everything we've discussed. Consider this. If our local distribution grids are already this heavily constrained and mathematically complex, just trying to deliver power to 30% of new cars, what happens in a few years when millions of EVs are enabled with vehicle-to-grid or V2G technology?
Oh, wow.
Right. We are about to turn every single parked car into a mobile power plant, equipped with massive batteries, actively trying to push energy back into this delicate, carefully balanced system.
A completely bidirectional grid. I mean, we will definitely have to save the math on that for another
It's
time.
a whole other puzzle.
It really is. But until then, keep questioning the everyday tech around you. The deepest complexities are usually hiding right in plain sight, just waiting to be plugged in.